Hey guys, it's Lauren. This is going to be your exam 3 review for Alexander's test on Monday. A few quick disclaimers. I did alter this exam. I took off a few questions, I added a few questions. All the answers are correct. However, I did take off one of the optimization problems and I added linear approximation. I also would like to add L'Hopital's rule is not going to be on the exam. I do have those questions. I did complete them, so I'm going to show you the solutions. However, it is not going to be on this exam, so it's not something you have to worry about right now. I also like to add I am not going to be doing any overt derivatives just because I don't want to waste too much time. So let's go ahead and get started. A point is moving along the graph of the function such that dx dt equals 3 centimeters per second. Find dy dt when x equals 4. So I always suggest you guys draw a picture. You guys know this from session. I always suggest trying to draw something to make your life a little bit easier. Now, whenever I plug this in Desmos, the graph looks essentially like this. My drawing isn't perfect, but that's kind of what it looks like. Additionally, based on the problem, you have a point and it is moving in this direction, the dx dt direction. And as it moves in this direction, you are experiencing the dy dt direction. So that's kind of it for the drawing. Let's go ahead and write down our givens and what we need to find. Again, I always suggest doing stuff like this simply so your problem is a little bit easier for you to parse through. So given, I'm given the function, I'm given dx dt, which is 3 centimeters per second. I'm looking for dy dt, so I don't know the answer to that. And I'm also given x equals 4. So let's go ahead and start setting this up. I would like to remind you guys I'm going to rewrite this so it is easier for me to solve. Okay. And then I'm going to set up my implicit differentiation. I'm always deriving with respect to t. If you are doing anything else in problems like these, you will be marked wrong. So, as a reminder, always d over dt for anything with related rates. So this is going to be dy dt equals negative 8x all over 4x squared 7 squared times. I assume you guys know how to get this answer, so I am not going to go through the whole rigmarole. Now it is a matter of plugging in x and dx dt to find dy dt. So let's do that really quick. Okay, now if you plug all this in your calculator, make sure you have parentheses in there, because if you forget them, then you are not going to get this point. So it should be negative 0. And then it's a long decimal, so I'm just going to stop it right here. I would say 0.019 is acceptable. But just for giggles, that is dy dt, and that is your final answer. Now, I will say I didn't see more than 2 related rate problems on here. They shouldn't be too terribly crazy. This one, the second one, is a little bit more similar to what you're going to see. They provided a picture whenever I pulled this problem from the book, so therefore, you know, a picture given to you. In the practice problems I saw from her, you did not have a picture, so I would suggest drawing a picture. Anyway, a light is on top of a 15-foot tall pole. A 5-foot tall person starts at the pole and moves away from the pole at a rate of 2.5 feet per second. After moving for 8 seconds, at what rate is the tip of the shadow moving? A, away from the person, and B, away from the pole. These are 2 different problems, so let's just go ahead and start off simple. Okay, so this is a case of similar triangles. So I broke these 2 down first. I got my bigger triangle, and I have my smaller triangle. And that kind of helps you see things a little bit easier. So 5 feet, 15 feet. Okay, so and then my givens, moving away from the pole, so that's this motion, is dx dt is 2.5 feet per second. Height of the light pole is 15 feet. Height of the person, 5 feet. I'm given time, which is 8 seconds. And then I'm also given the rate of the shadow, which I'm calling dsdt, or how fast the shadow is moving. I don't know that yet. Okay, so the rate the shadow is moving away from the light bulb, so going from here to here, is this x plus t. So let's start with relating these two. So this whole thing is x plus s, excuse me. But also, this is simply just s, because this is the shadow, like they show in the picture. This is the whole length. So x plus s, again, similar triangles. X plus s is the whole thing. This is 5, this is s. So let's go ahead and relate the two. Making a proportion be 15 x plus s equals 5 over s. I want everything to be on one side of the equation, and I want to get an s equals equation. So let's multiply x plus s. Okay. So essentially this is saying the length of the shadow is always half the person's distance from the pole. So okay. So now I'm going to go back to black. D over dt s equals okay. So to find the rate of the tip of the shadow moving away from the person, I am going to plug into this formula. So that's ds dt. That's how fast it's moving away from the person. So if I plug in one half, and then dx dt is at 2.5 feet per second. And that will be 1.25 feet per second. And that's the rate at which the shadow is moving away from the person. That's this right here. So now I need to find away from the light pole. So that is going to be this x plus s, which is just going to be d over dt y equals d over dt x plus s, which will be dy over dt equals dx over dt plus ds over dt. So again, what we just found is going to give me, I'm going to utilize this answer and this answer. So dy over dt equals dx over dt, which is 2.5 feet per second, plus 1.25, which is going to end up giving me 7.5 feet. So it's kind of hard setup, kind of a little bit in depth. I don't know if she's going to end up keeping those questions, but it's good to kind of be aware that it could be on there. Okay, let's go ahead on to the next thing. This is what I consider the meat and potatoes of this entire exam. So for A through C, find all critical numbers. If there are any, find the open intervals on which the function is increasing and decreasing, and apply the first derivative test to identify all the relative extrema. So that's a lot to go through. So I'm going to do A, B, C individually, go through it, kind of talk about everything. Okay, so to start off, I want to find the first derivative. I always just find the first derivative first. It's the easiest part of this whole thing. That's gonna be 2x minus 6. Now to find critical numbers, you set your first derivative equal to 0. So your critical value is going to be 3. So for this one, you have the test intervals -infinity to 3 and 3 to positive infinity. So what I like to do is pick a number for here and pick a number for here. For this one, my test value is going to be 2 and 4. I always used to do a chart. That's how I am the most comfortable, so that's how I'm going to do this today. So negative infinity is 3. Three to infinity. So again, my test values, sorry, excuse me. I actually made this 0 to make my life easier. 0 and 4. As long as it's lower than 3, it really doesn't matter. I just picked 0. And that was a miscopy on my part. So now for this, I'm going to plug in 0 in the first derivative. When I plug 0 in the first derivative, so 2 times 0 minus 6 is going to give me -6. Okay? Same with this one. I'm going to plug 4 into the first derivative. So 2 times 4 minus 6 is going to give me 2. Therefore, since this is negative, you're decreasing here. And since this is positive here, you're increasing here. And that's it. Now, because I go from decreasing to increasing, I'm going to have a relative minimum here. At 3. So to get my actual 3, like to get my actual minimum, I'm going to plug it into my original function to get -9. And that point, my relative minimum, the actual point will be this point. So if I go from decreasing to increasing, it's a relative minimum. If I go the opposite way and it starts out increasing and goes to decreasing, it's at a relative maximum. And I'll do the same thing for the next two. Okay. So I'm going to go ahead and erase these, and then we'll continue. Nothing too crazy. On the exam review, I saw a ton of questions like these, so being super comfortable with how to do this, I always set up a table. Sometimes she will give you, an interval, which makes life a little bit easier. And whenever you're testing that, you will test the interval as well. Okay, let's do number 2. Again, I always do the first derivative first, which I actually rewrote this. like that, which I can do. I'm just taking this 5 out and moving it so then that way it's easier to do. Which then would give me the first derivative of x to the fourth minus 1 to find critical values, or critical numbers, excuse me. Put that up here. Set it equal to 0 and solve. Now, because I essentially have to not cube root, whatever the next root up is, root to the like fourth root, I can do that, but then it's going to be plus or minus 1. Okay, so that means you have more than just the two test intervals. You're going to have 3. Okay, so now your new test intervals are negative infinity to -1, -1 to 1, and 1 to infinity. Okay, so again, I am simply going to pick numbers within that interval. So negative infinity to -1, I picked -2. From -1 to 1, 0. 1 to infinity, I picked 2. Now I'm going to plug those into my first derivative. So -2 to the fourth minus 1 will give you 15. F to the 0. It's going to give me -1. And then f to the 2 is going to give me 15 again. So increasing, decreasing, increasing. Okay? And I'm just doing those errors because it makes my life a little bit easier. So again, it goes from increasing to decreasing at 1. So that means I have a relative maximum. So if I plug -1 in, I'll get 4/5. So sorry, that should be a minimum, excuse me. And then decreasing to increasing. At 1. Be 4/5 as well. Okay. So let me just clarify really quick. Increasing to decreasing will be a minimum. Decreasing to increasing be a maximum. Okay, so, and define your actual points. Plug it into f of x and solve. Okay, so not anything super crazy hard, just inconvenient. Okay, so I'm gonna get rid of some of this work over here and start on this very last thing. Again, she will ask you, and then whenever you say, oh, what intervals are increasing, you're gonna say, oh, this interval's increasing, and this interval's increasing, and this one's decreasing. So whenever she asks you to list them out, you want to list every single one that is doing the thing she's asking you for. So do not forget, or else you will not get points that you should get. Okay, I'm gonna get rid of this now since I have had it up for a second.
For the Hesse? Mm-hmm. No, I didn't.
Okay, for this one, it's just power rule. It's really gross. It's gonna be
I think I'm really. It's on the third. Yeah. Oh. Yeah.
1/3. So, and again, if I want to set this equal to 0, I can factor this out. So I would factor out 1/3, 4/3. You can pull out 1/3 x to the third because they're both 1/3, x minus 4, and then I will set each piece individually equal to 0. So x equals 4 for this one, and then for this one, it's also just going to be 0, which makes life a little bit easier. Those are my critical numbers. So my intervals now are going to be -infinity to 0, 0 to 4, and 4 to infinity. So again, pick test intervals in between these. -infinity to 0, I picked -1. 0 to 4, I picked 1. And then 4 to infinity, I picked 8. Don't know why. You can just pick arbitrary numbers. It really doesn't matter. So for this one, so if I plug -1 into my derived equation down here, why did I not write that down? That'd be really helpful. I know it's a positive number. How about that? So therefore, increasing, this one is decreasing, this one is increasing. If you guys want to fact check me and double check, please feel free. I don't remember why I didn't write this down, but I didn't. I just wrote down my arrows, I think, because I didn't have a ton of space. So I kind of fudged it a little bit, but I promise they're right. So again, that's that. My test intervals that are increasing are -infinity to 0 and 4 to infinity. My one that's decreasing is going to be 0 to the 4. So now I want to know my relative max. That is when I go from decreasing to increasing. That's my relative max. And my relative min is increasing to decreasing. So to find that, I'm going to say 0 equals, and that's going to give me 0, and then 4, and that's going to give me negative 2.72. So my relative max is 4, 2.72, and my relative mean is 0, 0. Now again, when you are doing all this, you can check this with your calculator. It won't be efficient, but you can do it because these numbers are so small. You can also sit down and graph these. I do have a link over here to Desmos, but I don't think it will continue recording if I hop out of here, so I'm not going to. Okay, so let's move forward. For all A of Z, find the points of inflection and list the intervals of concavity for the given function. It says describe the tangent line. It goes through the points given. A question she asked was, is it horizontal, vertical, positive, or negative tangent line? And I couldn't find any good questions to go with that. So if you've heard that before, I'd study a question like that, just so you're aware. Okay, but again, don't get too caught up in it. Concavity means second derivative. Always and forever, okay? If you hear concavity, second derivative. Points of inflection are also your second derivative, okay? So my concern here is my second derivative. So I'm going to go through here. My first derivative is going to be negative 6x x squared plus 4 negative 2. And then my second derivative is going to be 6. Okay. So for this scenario, I'm really concerned about this numerator. Why am I concerned about it? Because that will tell me everything the function's doing. This will tell me if I set it equal to 0 where it doesn't exist. I'm not really worried about that right now. I'm very much worried about the behavior of the function. So this is what I want to do. Here's what I'm going to do. I'm going to set 6x squared minus 4 equal to 0. Divide by 6, divide by 6. Anytime I square root a function, it's going to give me a positive and a negative. So x is going to be plus or minus 2 root 2 over 3. Okay. So that is my point of inflection right there. If you write it with this little symbol, that's the same thing as writing 2 root 2 over 3, comma, negative 2 root 2 over 3. Again, I don't think she'd mind. That's also up to you. So we've done all that. We've done the hard part, okay? finding the point of inflection is probably the hardest part. Okay, now, to note, similarly to increasing and decreasing, you're gonna have intervals, test values, and whatever that's gonna equal, right? So whenever it's greater than 0, you're concave up. Okay, so whenever I pick my test intervals, this comes out to like, I think like 2 point something something, some decimal or something. So when I do my test intervals, I have interval negative infinity to negative 2 root 2 over 3. My test interval is negative 2. And I'll plug in negative 2. Same thing, negative 2 root 2 over 3 to 2 root 2 over 3. I think my test interval was 0. And then plug that sucker in. Give me some number. And then I got 2 root 2 over 3 to infinity. And I picked 2. So F. So I'm plugging all of these into the second derivative. It's going to go into this thing right here. Now, I would love to do all that math and give you all those answers, but I'm just going to kind of give you the quick rundown. So for this one, you're concave up, concave down, concave up, okay? So negative infinity to negative 2 root 2 over 3 and 2 root 2 over 3 to positive infinity, those are concave up. And then this one is going to be concave down. Again, I assume you guys can plug things into calculators, so I'm not baby stepping through it. If you guys have any questions, I would refer to my notes, your notes, anything like that. Just because I don't have time. I'm already at 40 minutes on this video. So I'm trying to kind of speed through this a little bit. So for this one, if she asks you to give her the intervals, these are concave up, and this is concave down. Okay, and that's what I would write. My test interval would be this, and that would be my answer. This would be my answer. This would be my answer. Okay. Please show all your work. I know that you guys can plug into calculators all of these numbers, but if you do not show the process, if you don't at least write down that you know you're plugging into here and you get some number, then I cannot guarantee you'll get points. Again, if she does it a little bit different than me, totally fine. Do it how she taught you. Do it how you're comfortable, okay? And do it the way that'll maximize your point grabbing, okay? So number 2, again, speed through. I'm just going to give you the second derivative to make life a little bit faster. Be negative 48x minus 4. Again, if I set it equal to 0, that's going to give me x equals negative 1 over 12. Okay, that's my point of inflection. That's an answer. She'll ask you for that piece. So do not forget those things. Now, I just have two test intervals, so negative infinity to negative 112, and then negative 112 to positive infinity. So again, create a little chart. My test values were negative 2 and 2. Plug those into your second derivative. Should be something like a negative and then a positive. Yeah. Okay, so this is concave up and this is concave down. Okay. I would probably write concave up and concave down, but for this scenario, you know it's because I'm telling you. Okay. So plug negative 2 back into here, plug 2 back into here, whatever that's going to end up being. If it's greater than 0, you're concave up, less than 0, concave down. Okay, same old, same old. If she asks for which interval is concave up, negative infinity to negative 1 over 12. If you're asking for which one's concave down, negative 12, 1 over 12 to infinity. Not too bad. Not too bad. I don't think she's going to give you crazy hard functions to do, purely because you guys only have like 2 hours to do this test. So I'm thinking you will have intervals that are similar to A, B, probably even C. I think C is probably a fair game question. Okay, let's go. I'm just going to give you second derivative to make my life a little bit easier. That's going to end up being 1 over x squared plus 1 to the 3/2. Okay? Again, now here we are. We are at an impasse because I have places technically, I guess, that I could set the denominator equal to 0 and it might not exist. But my numerator is just a 1. It's constant. If my numerator is constant, there's no changing. There's no changing. There's no point at which f of x, the second derivative of the function, is going to equal 0. And due to that, there's no concavity because it doesn't change. So, and because my denominator, not my denominator, because my numerator is positive, the function is concave up. Throughout. So throughout its entire domain, this function essentially just goes up. So, and the graph looks kind of like this. It's like almost an absolute value, but it's softer. But there's no point in inflection. It doesn't change. There is no point at which it goes like, there's no, oh, up and then down, and then there's a change somewhere, right? This is all the way up the entire time. Okay? So that's that one. That one's probably your easiest one, because if you get a second derivative where the function's constant, nothing's going to change about it. And if this was negative, they need to be concave down the entire duration of your domain. Okay? Sounds good. Not too terribly bad, right? Okay. Now, I took off C because I realized I misprinted. So ignore C. I'm going to do these really, really quick. Just so you guys have them, just so they're within your wheelhouse to go back and look at later. Because I don't want you guys to not have them. So really quick, always and forever. For indeterminate form first. First. Do that first. If I get 0 over 0, infinity over infinity, even infinity over negative infinity. I don't want that. That's bad. Okay, so x approaches 2. Simply sit there and go, okay, well, negative 2 cubed minus 7, negative 2, not negative 2. It's positive 2. Ignore those. And you will get 0. Bad. Don't like that. So 56 over 0. Again, I could be wrong, but you don't want that. That's undefined. It's not anything. So what am I going to do? I'm going to take the derivative of the top and the derivative of the bottom. And then I'll plug in again. So take the derivative of my top function. So that's just this up here. Again, not quotient rule. 14x plus 10 all over 2x plus 1. That'll give me negative 6 to the 5th. Okay, and again, that's after I plug this 2 back in here. No indeterminate form, so therefore you're good to go. Okay, this one. If I just plugged in sine 4 pi all over negative 4 minus 16, 0. And then this is like some crazy, like, decimal. But again, bad. No, sir, can't do that. So what am I going to do first? Take L'Hopital's rule. I remember being so mad when I first learned this because I was like, wait a minute, I can just do this and limits aren't that hard? Exactly. So the derivative of sine is going to be cosine pi w all over 2w. So pi and then this right here will just be 1, so it'll be pi over 8, be negative, excuse me, keep forgetting that negative sign, but negative pi over 8. Again, not much harder than that, just take the derivative of the top, and then the derivative of the bottom, and then plug back in your limit, and see what happens. Again, if it doesn't work the first time, try it again. You can do L'Hopital's as much as you need to. Okay. Question 6. I would like to clarify that I took out the previous optimization problem with the centimeters on wire. It got too complicated. It wasn't necessary. And I do not think it will be that involved. Okay? So, optimization is all about kind of steps again. So, the steps for optimization, I try to break this down as good as possible. Sketch. Draw a picture every single time. 2. Determine your constraint equation and your maximization equation. So constraint is like, hey, we have $750 and this is how much each piece is
per foot or whatever you want to call it. So that's my constraint, what stops me. I'm trying to maximize the area for this cost, okay? So let's just start there. So sketching, I got a rectangle. Made it really, really ugly, but it's okay. So 7 feet, $7 per foot on one end. $10 feet, $10 per foot on these two ends, and $2 per foot on this end. Okay, so my constraint equation is I have 10x plus 10yx plus 7y plus 2y to get me to $700 total, right? This is all my cost. So 20x plus 9y equals 700. Okay, that's my constraint equation. Okay, I need 20 times x plus 9 of y to get me to 700. So x, y, there we are. My maximization equation is area. So area of a rectangle is length times width, or in this case, xy, okay? Because again, length, width. So now I want to put my constraint equation in terms of either x or y. I chose y just because I like y. I want it to say y equals something, right? Put your constraint into your y terms. Whatever's easier, okay? So in this case, I decided to do it as y. So it's going to be y equals 35 minus 9 over 20x, okay? So subtracted 20x from both sides, and then divided by 9 all the way through. That's my equation, okay? So now I'm going to plug this into here. So a equals x times y, or a equals 35 minus 9 over 20 x times x. Okay, now I'm going to distribute that really quick. So a equals 35x minus 9 over 20x squared. Okay, so number 5, I'm going to derive number 4 and find critical points. So therefore, the derivative of a, and then I'm going to set that equal to 0. My x value is going to end up being 350 over 9, okay? And I'm going to plug So now I'm going to plug this in to my y. So my answers are going to be, oh no, this right here and this right here. So for all of these, so it'll be 350 over 9 times 35 over 2 to get you to that 700. And 20 lengths of x and 9 lengths of y will get you that 700 maximum. Like it'll hit that point just underneath 700 that you can spend. Okay? Optimization is kind of complicated. It's not my best, and I'm sorry if I can't explain it super well. My suggestion would be to go to Paul's online math notes and do a couple more problems and review his notes, just so you guys have a better understanding and a good foundation of optimization. I would just do those practice problems. Don't do the like extra optimization practice, just because it gets a little bit too complicated. And again, I don't think she's gonna make it too terribly hard. Okay, so let's move on to the last two. Okay, linear approximation. So what is linear approximation? We're essentially using the tangent line of a function at a specific point to estimate the function's value near that point. So let me draw this out. So I'm given a function, so it looks like that, right? And then their tangent line looks like this, okay? And I can say, okay, well, at this point right here, how close am I? That approximation, how close is it? So, and determine that formula, it is
It's supposed to start soon, but she's finishing up her session.
if you want, you can hand out the practice test and you guys can get started.
I was gonna say, is there another one that doesn't have like the answers and the questions?
Does it have the answers?
Yeah, like, well, for some of them, like, all the way to 17 is good, it's just 18 through the rest has all the answers.
Are you kidding me? No, that's how I printed it. I thought I fixed that.
I'm sorry.
Oh, okay.
Oh.
This is a biggie for this one, right?
Yes, it's biggie, yeah.
Yeah,
It looks just like,
yeah, that's right. It's the, but it's not. Okay, this must be the temporalis muscle here.
yes, the right by them.
Okay. So those are all your really, really important things, right? So to find linear approximation, the first thing I want to do is take the derivative. So step one. So
Okay. But if you just know temporalis, because your temporals right by the ear, you'll be able to.
Okay, so it says number 8.
Number 8 says the superior.
that's the first derivative. Okay.
It's not the model.
The other one. The other ones
So to find all of these pieces to do your linear approximation, you got to go ahead and plug 5 into the derivative and just the original function.
I see it now.
Yeah.
This is not correct. That's what, but here's my point.
I don't even speak the temple. I don't know.
Okay, then
The book. Okay, yeah, definitely. The book. It's more accurate. People who make those, I don't even think they use with anatomy.
Okay.
So,
So I did that. I did it without doing this all for you guys. I assume you guys can plug in really quick. And then oh wait, excuse me. And that is the linear approximation at x equals 5. Okay. Now, I saw a question like this on the exam. I don't really understand how it all works. Okay, so I'm just going to show you how to do the general steps. To find this piece, you're going to do 1.08 minus 1, 0.08. And again, it should be the same for every single one. Every single time it'll be this to this one. You are going to, that is, so essentially you're going to compute this and this individually. Which is just plugging them back into the original function. This is going to be negative 0.0672. This is going to be 0. So to find the change in y, negative 0.0672 minus 0 is going to give you that's that answer. That answer. And then for 3, dy. Essentially is just y prime 1. So find the derivative of this, which is going to be 4x minus 5. So then you're just going to plug 1 in there. So 4 times 1 minus 5, negative 1. And then the y is y prime 1 times the change in x, which you found up here. So negative 1 times 0.08 is going to give you negative 0.08. So this is dy. this is change of y, and that's change of x. Again, I'm not super familiar with linear approximation. I did not learn it. I would suggest going on YouTube and finding a resource to kind of get you started. Okay, and that is the end of my